Thank you. Thank you all for being here. Jose asked if I was okay with being interrupted. I'm okay with being interrupted.
No.
Sorry,
Don't say that. No.
But if it's veering wildly off course, I'll redirect. Okay. For clarifying.
Thank you.
So thank you for the invitation to come. Thank you for coming. And then also thank you to my co-researchers, Nicola Michel and Emmylou Hefner. This is work we've been doing together since late 2022. And this is based on an even larger collaborative project around Oswald Veblen, the American mathematician. Marco, you inquired about this yesterday. How big is this archive? It's 13,800 items. How they're counting items, I'm not quite sure. I don't know if that's pages or if like a book could be an item, but it's quite extensive. So, and that's actually just his archive that's housed at the Library of Congress. He also has materials at Princeton and the Institute for Advanced Study. So the motivation behind this collaborative historical research project was the vastness of Veblen's archive, as well as his significance for 20th century mathematics. His correspondence includes communications with people like James Alexander in topology, G.H. Hardy, Oppenheimer, Bertrand Russell, John von Neumann, etc. So many huge names in the history of 20th century math and physics. If you are interested in the history of these individuals, there's probably something of relevance for you in the Veblen archive at the Library of Congress. I have some of them digitized, so feel free to shoot me an email afterwards if there's a specific person. I obviously don't have everything digitized. I couldn't get around to that entire corpus, but I'd be happy to share the materials that I do have. And so Veblen was an enormous figure for 20th century mathematics, not only his mathematical contributions, which is what I'm going to be discussing today, his work in the axiomatic foundations of geometry, but also his work for institutionalizing American and indeed international mathematics. So different contributions in this collective research project focus on, for example, the foundation of the Institute of Advanced Study in Princeton, for which Veblen was really instrumental in actually the particulars of the design. I was joking about the volume of television screens in this room. Veblen would not have been okay with that. He was like micromanaging in-room design, and he was very attuned to exactly how spaces are used and being very precise about that at a level that's quite surprising for someone who's a research mathematician, that he would be that invested. But he really was committed to mathematical collaboration from the very beginning of his career, and initially through his own research, but then actually through institutionalizing spaces for mathematical collaboration. And so while I'll be talking about his mathematics, I just want to highlight the fact that these impulses reverberate through his work, both personally and politically and mathematically. So what I'm going to be focusing on today centers on a specific object. This is Veblen's notebook from a class he took at the University of Chicago, autumn 1901, with E.H. Moore, who was the chair of the department there, on the foundations of geometry. This class is a direct response to Hilbert's Grundlagen. And so it was an effort for a select group of students, graduate students at the University of Chicago, to engage with cutting edge German research, mostly German, some Italian as well, research in postulate analysis. And it ended up being extremely fruitful. So just to highlight some of the texts that fed into this treatment. So these are just some of the texts that are explicitly cited in the notebook. So we know these were, if not being read, at least being disseminated. So the work of Schur, Pieri, Peano, Forti, Hilbert. There are others. This is just a sample of the works that are informing this term. And then on the other end, there were texts that emerged directly as output from this seminar. And we know not just based on the mathematics that contained, but actually explicit citations to this seminar. So I'm not sure how readable that is, so I'll read this. So the first is from 1902. E.H. Moore publishes On the Projective Axioms of Geometry. And in a footnote, he says, this paper has been prepared in connection with my current Chicago seminar course on the foundations of geometry and analysis, and queries and remarks of members of this course, in particular of Mr. O. Veblen, have been a source of much stimulus. So his graduate students being cited there, and then this course, which is actually an unusual move, right? We don't often see courses being cited. 2 years later, Veblen publishes his dissertation, and again, he explicitly cites this institutional network at Chicago. I wish to express deep gratitude to Professor E.H. Moore, who has advised me constantly and valuably in the preparation of this paper, and also to Mr. Lennis and R. Elmore, who critically read parts of the manuscript, and they were all in these seminars. And then in 1905, Veblen has another paper on plane curves and non-metrical analysis statistics, and he again points directly to this course. This case is under discussion at the University of Chicago in 1901-02 in connection with Professor Moore's seminar on foundations of geometry. So it's a really important seminar for research at Chicago at this time. So my talk is going to be in 3 not evenly divided parts. I'm going to start just by grounding some of the context of what was going on at Chicago in the 1890s and 1900s to get a sense of who was there and why these seminars were happening. Then we'll look more deeply at Veblen's notebook. I'll do this in 3 parts, sort of 3 different ways in which we can learn about axiomatic collaborations through Veblen's notebook, so close looks at 3 different cases, and then draw some broader conclusions about collaborations in mathematics and seminars as well. So this map of the United States from 1890 is useful in situating the population density because it's quite different then than it is now. And what this highlights, among other things, I mean, we could spend the whole 2 hours on this map. There's a lot going on here. But what I want to talk about in particular is that you can see the Northeast certainly has the most dense population. And while Chicago itself is quite dark, the rest of the Midwest is much lighter in color. And what's happening at this time is not only the United States trying to catch up with Europe, but also the Western United States, which Chicago is considered Western, trying to be recognized as a legitimate institution or region by the Northeast, right? So the Northeast has these older universities, and University of Chicago starts in 1891, and there's a bit of legitimacy happening here in trying to establish it as a serious research institute. And I won't be drawing on this language in my talk, but there's certainly quite a lot of conversation among mathematicians about trying to establish Western mathematics as a legitimate space for mathematics. So as I said, the University of Chicago began in 1891, and initially the faculty consisted of 3 people. E.H. Moore was the chair of the department. He was an American mathematician. He got his PhD at Yale doing some non-Euclidean geometry, sort of British style non-Euclidean geometry in 1885. He was at Northwestern when he was recruited to start the mathematics department at Chicago. And then as chair of the department, he had some input for hiring his 2 associate professors. So he selected the German professors Maschke and Bolze, who were both already working in the United States. And then they come to Chicago. And they're a very powerful trio. So in Veblen's own words, this is 1933. Moore's just died, and Veblen's reflecting on his time at Chicago. And he notes, as I look back at it now, the most remarkable thing about Professor Moore was the way in which he brought the most modernistic mathematics of his time to us. He was like the conductor of a symphony orchestra in an American city at the present time, when the knowledge and appreciation of music is still at a very primitive stage, who nevertheless manages to get a performance of the latest Russian music out of his orchestra in such a way that is, to some extent at least, understood by his audience. It's a bit of a labored metaphor, but I think his point is he's actually making a really interesting comparison to modern music, which is quite interesting. But he's saying, like, you know, Moore was working with what he had, and it wasn't the best of the best in mathematics at this time, but he really was able to do something with it. Similarly, so an excellent historical source on the University of Chicago at this time is the book of Karen Parshall and David Rowe from 1994. And speaking about the mathematicians at Chicago, they say the Chicagoans realized that for their program in mathematics to attract the cream of American talent, its offerings had to rival those of the ever-attractive German institutions. Thus, they fashioned a course of studies intended to give the student a comprehensive view of modern mathematics, to develop him to scientific maturity, and to enable him to follow without further guidance the scientific movement of the day, and if possible, to take an active part in it by original research. So they're directly and explicitly trying to emulate German institutions, and they're trying to foster original research among their students. And so it's completely unreadable on this screen, but I'll just tell you about it. So one way they did this is with course offerings. And so this is just from the 1901 course catalog to give just a selection of the courses that are being offered. So there's a course in quaternions, twisted curves and surfaces, pure projective geometry, analytic projective geometry, modern analytic geometry, higher plane curves, algebraic surfaces, Lee's theory of differential equations, continuous groups, invariants, functions of a complex variable, etc. So if you consider the fact that there are they have some assistant professors this time, but it's still quite a small department. And this is a very robust, this is just a selection of the graduate course offering. So it's pretty impressive, the variety of classes that are being offered. Yes.
Am I reading a course in the first column, mathematical reading and research?
Yes, that is right. So, and it says, when it is advisable that students undertake definite mathematical reading and research not closely connected with any current lecture, course, or seminar, this work will be directed by one or the other of Moore, Boltz, and Mashka. So they even have like an open space for students who want to do something that's not offered. And in fact, we could identify the course that Evelyn takes the notes of as a course of this kind. Yes,
Did you count how many preparations they had per year?
I haven't.
But that's interesting.
No, it would be interesting. Yeah, and I mean, some of these courses aren't offered every year. You'll see there's parenthetically saying not offered. But certainly someone could absolutely do that and see. I mean, it would also be interesting to see the patterns over time. It's a good undergraduate research project. The other thing, so besides course offerings, the other feature that Chicago creates, which is very helpful, is to fund graduate students through fellowships. And so this is the language from one of the years that Veblen was a fellow. The other fellows are not as well known. And I just want to draw our attention to the qualifications and expectations of the fellows. So there are usually 3 or 4 of them. They're assigned to those students excelling in their mathematical acquisitions and scholarly abilities who exhibit strongest evidences of marked creative ability in mathematics. It is a distinct advantage to candidates who have been at least 1 year residents at the university, so not students who are just arriving. They have to file some paperwork with the president, and then fellows agree not to give private tuition and may be called upon for assistance in any departmental teaching or other work. In no case, however, will a fellow be expected or permitted to devote more than 1/6 of his time to such service. So it's really a protective measure so that students aren't teaching too much, so they have time for their research because they're being identified as having research potential, and they may also be good teachers, but that takes time, and so that's part of what's happening. Okay, so the class I want to be talking about is the foundations of geometry, and so this is from a document housed at the University of Chicago that lists the courses and who is in attendance. They're handwritten, presumably they're accurate. They're handwritten all by the same person, so I think someone compiled it at some point. So the first offering of the foundations of geometry and analysis says was not listed in the course catalog. It was a last minute addition. And the participants are Jordan, H.E. Jordan, W.W. Hart and Veblen, I think worked together at some point. Alice Gray, Oswald Veblen, and W.O. Beal. And then that's the last one, W.O. Beal.
Okay, it's not.
Yeah, I haven't.
I was reading Borelli. But a little
Oh,
bit
that would be a very different story. Yes.
strange. It was a
They're all
little bit
graduate
strange.
students at the time. And the course was then offered the following summer more officially. And so I have that language on the right. And so the course is described as geometry, as a purely abstract deductive science. Right? And then the prerequisite is quite interesting. It's an unusual prerequisite in that if it's not a course, it's just a facility in abstract mathematical reading, which I wish I could list that for some of my courses as a prerequisite. That's quite a nice one. I think it carries over as being. So what did the notebook look like? So I'm going to just go through some images of the notebook. The first thing to highlight is that Veblen took lecture notes always on the right-hand side, and he left the left-hand side blank for later marginalia, and we'll see an example of that shortly. So the lecture notes can be quite formal and polished looking in this case. His handwriting is pretty readable. And he's often citing different authors or texts. So these are some of Terry's accents.
He's explaining why there are so much items in the. He's explaining why there are so much items in their shoe because half of them were blank.
Yes, but so yes, I don't know if they count the blank items. That's a good point. When I paid to have this digitized, I was very disappointed in the number of blank pages in this notebook that I paid for. But that's okay. I didn't know. I mean, that's, part of the gamble. Here's a more interesting page in a way, because you can see that now he does have writing in pencil on the left, where he has some axioms that he's working with. We'll return to these, that he's written on the right, and then he later comes back and is rearranging them. It says on the top left, rearrange, and then a different set of numbers. And then there's a later note that says note April 9th with further thoughts on this. So you can see this is document he's returning to over time. Yes.
Is this the sketch work of his thesis? I mean,
Yes.
he's taking this in 1901.
Yeah.
And when was the thesis done? Like 1 year later?
So it's published in 1904. I don't know how much changed over time because I don't have the earlier version. He first presents on it in 1903. We'll look at there's a documentation he presented on it, but suggestion that what he presented wasn't complete, like he added to it afterwards. But absolutely, yes, that is part of my intention today, is looking at how it is scratch work for his thesis. It absolutely is. And it's scratch work over time. For example, when it says note April, I don't know if that's April 1902, it could be April 1903, right? There's an indication that he's coming back to this and revising it. And then most intriguingly this doesn't happen very often, but rarely in the notebook, are other pieces of paper, clearly notes taken when he's not with the notebook, but feels that this is relevant to that research, that he's then pasting into the notebook. And on the right is maybe one of his students' work. It says Edith Simpkins, and it looks like calculus homework. So I don't know if maybe he got someone else's notes and then realized that he didn't want it, but that's also glued in. And the notebook begins, so this is the first page beyond the title page, with a pretty programmatic statement. A mathematical science may be regarded as consisting of a set of symbols, a set of relations, axioms connecting the symbols, and a set of deductions reached by a finite number of logical steps. And this is very, very clearly drawn from Hilbert's 1900 Paris problems. So this is the translation by Mary Winston Newsom, who was also a Chicago graduate student and then ended up going to Göttingen for a while to work with Hilbert. And you can see there's really nice alignment here in Veblen's language and then the language of Hilbert's Paris problems. So saying that problem arises from mathematical science to investigate the principles underlying these ideas, and so to establish them upon a simple and complete system of axioms, that the exactness of the new ideas and their applicability to deduction shall be in no respect inferior to those of the old arithmetical concepts. To new concepts correspond necessarily new signs. And so you can see the alignment with the importance of symbols here. Symbols are signs, the importance of having an axiomatic system, and then deductions as well. Okay, so now that I've looked this quick introduction to Chicago, quick introduction to the course, to the notebooks, I now want to talk about the contents of the notebooks, and I will be doing this in 3 parts. So starting with simplifying and proving an axiom. And then we'll look at some more notation around result about the triangle of transversal line, and then some of the meta-theoretical concepts of independence and categoricity that emerge from the notebook in Veblen's dissertation. So in Hilbert's Grundlagen, the 4th axiom in the axioms of order are that any 4 points A, B, C, D of a straight line can always be so arranged that B shall lie between A and C and also between A and D, and furthermore that C shall lie between A and D and also between B and D. And if that is hard to follow, you can look at the figure which shows those 4 points. So it's basically an axiom about naming points, right? Naming points in a certain order. And famously, E.H. Moore, in his 1902 paper, shows that this axiom is redundant, right? So it's a correction to Hilbert. And this is how he begins the paper. He says, I'm going to show that this axiom is redundant. And I'm not going to go through his proof, but I do want to highlight some of the features here. So he does this by making 4 statements, which if I read would, well, I don't know about the rest of you with the retaining of like random associations of points, but for me, it just goes out the other ear. So I'm not going to read these axioms, but they're all about point order. And then he says that these 4 statements are evidently equivalent to Hilbert's linear order axiom, and then he restates the axiom I had on the previous slide. And the way that he goes about, and then he says that he's going to show that these statements are theorems of a geometry in which axioms and then some number of axioms hold. So he is going to show that Hilbert's axiom is a rule of these four statements, and these four statements follow from earlier stated axioms. Thus, Hilbert's axiom 2,4 is redundant.
And
And
that is strange to write in the statement of a theorem, evidently.
yes, yes,
Because
Agreed.
evident that you have not to prove it. So I never saw something like that. Evidently, in a statement of a theorem, it's quite strange.
it's not the most beautiful part of Moore's text. It's a little messy. I mean, he keeps breaking it into more and more subcases, and then eventually it sort of concludes and you don't really remember where you were when you began. But what he's going to then do is show that that his axioms that he stated so far lead to if ABC and ACD, then BCD. So a shorter statement, and then he's going to get everything else from that. But what I actually want to focus on is not Moore's main text, but his footnote. And in the footnote, he says, Mr. Veblen has found that Hilbert's axiom 2,4 is deducible from the statements if ABC and ACD, then ABD, if ABD and ACD, then ABC or CBD. So it's somewhat of a throwaway aside. He doesn't actually talk about Veblen's proof, but there's a suggestion that they've been talking about this and that Veblen has played some role contributing to it. And indeed, if we look at the notebook, so pretty early on, this is actually, some of the pages are not numbered, but this one is page 23. He has a simpler form for 2,4. This somewhat breaks the left-right rule in that this is something where it's work that's on adjacent pages. He's sort of interrupting the lecture notes to work through this. And you can see he's devised, so some features I want to highlight here that are quite interesting is, first of all, you can see he's using this very clever graphical diagrammatic notation where he's aligning the points so that there are gaps where those points are going to fall in. So it's actually a quite nice way of quickly summarizing these order properties that makes the deductions more followable. And you can see he's maintaining that throughout all of these derivations. So he has this simpler form, 2,4 prime. If ABC and ACD, then BCD. This is what becomes 2,1 in Moore. And he needs to, if he's going to say it's a simpler form of Hilbert, well, he doesn't actually establish simplicity. It's certainly fewer words than Hilbert, but I think it's arguable whether it's simpler. However, he does have to show if it's another form that it's equivalent. And so he does not say evidently, but he does prove that if 2,4 prime, then 2,4 follows. So this proof is on the top right, and it's by cases. He has 3 cases, and then each of those cases relies on these sub-theorems that he has, alpha, beta, gamma. Each of these sub-cases relies on deriving a contradiction. So he supposes the 2 alternative orders that could follow if not the order that he wants, and then shows that each of those orders reach a contradiction. Another interesting feature to this, besides the notational choice with this alignment of letters to denote the point order, is you can see he's doing this over time, and it's not polished, right? So he has something crossed out, and then you can see at the bottom, theorem gamma is really squeezed in there as if it's a later addition. And in fact, theorem gamma is required for I don't think I can, well, actually here. So you can see here, it says by gamma. So later he realizes he needs this result and then he adds gamma at the bottom. And then these results here, case 1, case 2, case 3, case 1 relies on alpha, case 2 relies on beta, and case 3 relies on alpha. So gamma, even though it's given the same status as alpha and beta, is actually like a sub result that's only being used in beta. So it's interesting to see Veblen working through this problem as a young student, and developing notation on his own, and then sort of adding theorems to make it work. And then Veblen will repeat this result in his dissertation. So his dissertation is published in the Transactions of the American Mathematical Society. This is one of the leading math journals in the United States at this time. And it's published in 1904 as a system of axioms for geometry. And his theorem 9 is the proof of the redundancy, or well, it's replacing what was Hilbert's 2-4. And he notes that again in a footnote, he says this proposition was given as axiom 2-4 in Hilbert's Festschrift. Its redundancy as an axiom of Hilbert's system 1 and 2 was proved by E.H. Moore, and then it was also later proved by R.L. Moore, confusingly, two mathematicians with the same last name doing the same thing, but no relation. So interestingly here, he's dropped the symbolic notation that he employed in his notebooks. When interesting two-dimensional notations are dropped, it could always just be a result of publishers complaining, right? So it's not quite clear why that's abandoned in this context. It's easier to do by hand than to typeset it. So it's just stated as to any 4 distinct points of a line, the notation ABCD may always be assigned so that they are in the order ABCD. So this is more or less equivalent to Hilbert's axiom 2-4. I would argue that it's more comprehensible, actually, the way that it's stated. It seems clearer and cleaner to me. The proof is also involving many subcases, and it aligns quite clearly and cleanly with the proof in his notes from 1901. You can see the theorems alpha, beta, and gamma are all present as actually numbered lemmas. There are more lemmas. It's not just those, but they all sort of survive into this later published work. And so you're seeing in the context of this research seminar, Moore and Veblen collaborating to some extent, working through this problem, which ends up then bearing fruit in both of their work. And I would say that this is actually the part of Veblen's dissertation that bears the strongest resemblance to the work of Moore. It most closely resembles Moore's work. So there's a real tightness.
Sorry, it's very possible that what I will say is a completely stupidity. But in his notation, is simply, it seems to me that is embodying a sort of order. So the very idea that ABC, CD, and ABC, there is an order in ABT. So the graphic order. Okay, so it seems that he is not explaining what is an order. He is explaining that the geometric order corresponds to the graphic order. So to say, he's supposing that we know what is a graphic order.
Yes.
And we transpose the graphic order in the
Graphic, you mean that the letter B comes after the letter A, the letter C?
Yes, I mean, it's not explaining what is an order.
Yes.
It's supposing that we know what is a particular order, that is the graphic one. And we say that the same order also apply in geometry, or it's totally stupid what I'm saying.
I think you're right. He never explained what it means that the letter B appears after the letter A, but I think
This is what we call order.
yeah.
So I would expect.
It must systematically relate to the betweenness relation, right?
Yeah, and I don't have this document, although I could pull it up, but I mean, he does talk about order more explicitly at the beginning of the text. This is about halfway through. So this is not the first introduction of order in the text.
But it's betweenness in the end, right?
Yeah. Okay, I'm happy to pull up that and we can look at him from page 1. I feel like it's a little unfair to start critiquing sort of halfway through the text. I'm also happy we can come back to this in the Q&A and look through the proof in more detail.
So I want to say, if we explain what is an order, we explain something about, I don't know, the injectivity of a function, or we make some abstract definition that now I cannot imagine now a definition of order, but certainly will involve the notion of injectivity of a function, something like that. Here, no.
Yeah, you're right.
I know what is an order.
Yeah.
Look,
Yeah.
ABD, this is an order.
Yeah, it's about betweenness, absolutely. And I mean, he does also explain like, hey, I'm going to use some geometric terms loosely. And yes, but the way you're thinking about order is definitely not.
Is order for him the notion of betweenness in this case? What does it mean, ABC? Means between A and C,
Yeah.
that's all.
Yeah.
That's all it means.
Yeah.
That's
So it's a predicate, it's a notation for the predicate.
Right.
He is in between A and C,
Right.
so, and he gives the axioms for that. So this is just, you can read that as a notation for the
Right,
predicate.
that's the way I was
That's
thinking.
it.
Axioms of order. All right. So this is just this is a summary of someone else's axioms. So just to conclude from this section, the notebook in this case emphasizes interactive and collaborative process of proving that Hilbert's 2-4 as a theorem. And then there is certainly a relationship between this idea of finding a new, maybe simpler version of an axiom and showing an axiom that's redundant. This initial questioning of, so in Veblen's notebook, he's not saying axiom 2-4 is redundant, but he's saying we could replace axiom 2-4 with something else. And you can see that that is sort of a first step towards sort of, do we even need this axiom? And then the last thing is just about notation. Veblen's efficient and fruitful notation from 1901 is condensed into a more abbreviated form. I think thinking about order as a notation actually is quite useful in that case. So that brings us to a second example. This one's going to be slightly briefer, and this is concerning other notational strategies, but now in published works. So this is from E.H. Moore's paper, and as we know now, this paper is resulting from this lecture that he, or this series, this seminar series that he's giving with Veblen. And in it, he has an axiom, axiom 4, the triangle with transversal line. And it is a line which cuts one side of a triangle externally and another side internally, cuts the third side internally. And then Moore restates himself, which is actually going to be really hard to read aloud because of the notation, but I'll do my best. If A, B, C are 3 noncollinear points, and if the line DF, or under that he has DE, cuts the lines BCAB, or under that BCCA in points DF or DE respectively, then I'm actually going to stop reading this. It's very hard to read. I think it goes to show that sometimes notations are not meant to be read aloud. But you can see that he's putting points and lines above each other. So there's something sort of like a duality happening in that sense, which with this nice use of notation. I will point out, actually, strikingly, in his personal correspondence, E.H. Moore also does this. So he'll be like writing about something not mathematical, and I'll put like 2 adjectives on top of each other, which is really funny to see that sort of the mathematics has pervaded it. Okay, so the result is that we have a line, and I'll just say CA is cutting in a point E such that CEA. And so you can see there's the 2 different configurations here. And then he says notation, we denote the axioms into which axiom 4 has just been analyzed by the notations 411, 412, 421, 422. So take a look at this. It's quite small. Can you make out what the 4 parts of this axiom are? The 2 parts are quite clear. There are 2 triangles. But what are then the 4 parts?
It's depending on whether the E is exterior to the triangle or not. Right, because the original triangle is ABC. So you have to keep that in mind.
Mm-hmm.
So in the second figure, F is external to the triangle.
Yes,
Well,
that's
rather E is external to the, and it's incident to the triangle in the first figure.
yes, that's the difference between 4-1 and 4-2. Yes. But then he's
Oh, and
further
then
subdividing.
further.
And so the fact that no one shouted this is giving me some validation. When I read this, I was like, I don't know. And he has a footnote that says, similar self-explanatory partitional suffix notations will be used elsewhere in this paper. I'm just like, you jerk. That's not self-explanatory. And so I was looking at this and I was like, what are the 4 parts? I mean, I could absolutely see the 2 parts, but then what are the further 4 parts?
But sorry.
And you may well get it.
Sorry. If I remember well, when in Hilbert thesis, he sent to me a version of passage. theorem of axiom. And in Hilbert axiomatization, Pache is an axiom of betweenness. It does not seem to be. So it's putting together two different parts of Hilbert. The Pache, the axiom of Pache, where it is in Hilbert, you remember?
2-4.
It's 2-4.
So,
Very good.
yeah, but what
So
happens?
is a axiom of order, Pache in Hilbert?
It's an incidence axiom, isn't it? so?
It's an axiom of incidence, not of order.
But he doesn't have lines. Hilbert has lines. He only can speak about betweenness, between points,
Okay.
and explain collinearity in terms of betweenness.
So the idea is to put together.
To explain
ask
past
the-
action using betweenness, I believe.
Okay.
It looks right.
So there is something deep
I see.
here.
Yeah.
Oh, cool. See, yeah, so I mean, I'm not saying it's impossible, but I don't think it's self-explanatory at the level. But what's interesting about this is that if you go back to Veblen's notebooks, it actually is much more explicit. And so
So, I'm sorry, so what was 411?
I'm going to tell you.
Oh,
Don't
thank
worry. Suspense.
you. You're leaving us like.
Yes. Okay. So if we look at the version of this in Veblen's notes, this is in his projective axioms of December 14th, 1901, and this is axiom 7. And you can see, hey, it's the same triangle. So it's the same triangle as figure 1. Is there slightly different lettering? So I've actually, if you compare Veblen to what I've written, I've translated Veblen into Moore's lettering for better recognition. But this is what Veblen says. If there exists none of the relations, 3 relations, whereas ABD and AEC BCF, then 1 E exists such that CEA and 1 of 3 different order options, F exists such that BFA and 1 of 3 different order options. And so I think it's actually much clearer here what the 2 parts to the 2 parts are, in that we have existence and then order. Right, so he's first saying E exists such that CEA, and then there's the order in which E exists with respect to F and D. And so it's much more clearly broken up than in when you read Moore. It's much less clear that one is giving you that point, and then the other one is giving you the order. It's much clearer to see that there are 2 parts here. And in a way, this suggests that Moore's understanding of what is self-explanatory is probably based on these intimate conversations in lectures with students, and not sort of with the wider public who might read his work. And then in Veblen's published version of his dissertation, this is now axiom 8, again, the same figure, triangle transversal axiom. And here he actually drops all the cases. So this is the version that you could reasonably read out loud, unlike the other ones. And so if we have 3 distinct points, A, B, C do not lie in the same line, and D and E are 2 points in the order B, C, D, and C, A. Then a point F exists in the order A, F, B, such that D, F lie on the same line. So it's not identical, of course, but it's playing the same role across these 3 texts. And you can interpret then this notation that Moore is employing by looking at Veblen's notes. So I'll just point out sort of a broader historical point that the perspicuity of notational strategies depends on the intended audiences here. So what Moore is calling self-explanatory may reflect actually a hidden local context of his publications. So in 1902, Moore is one of the editors of the Transactions. This is published in the Transactions. And the requirement for things to be published in the Transactions is that they had to be presented at a meeting of the American Mathematical Society. But the American Mathematical Society had just started having meetings, local meetings in Chicago. So it actually created a really easy venue for Chicago mathematicians to present their research as soon as they feel like they have a result, and then publish it in the Transactions, much more so than people outside of the Chicago or New York area where the meetings were taking place.
But there is not a supposition of continuity that the space is R2 and not a Q square root. Because if Q square root does not necessarily exist this point, or not.
You're intersecting only lines here.
So yes, because the question of intersection.
So lines are.
Intersection depends on the fact you are working on R2. If we're working on a Q square root of 2, we could not have intersection. So it's not too strong.
So it's
I think there is an assumption.
But Hilbert does not assume that the plane is R2. He assume in the last option, say, okay, we can assume it, but it's not necessary. We can make geometry also in
But
direction.
you're not assuming that here either. You're just working with lines. Intersections of lines, that's a linear, so it's a linear equation, some linear equations. So
Yeah.
you're going to have always solutions. You're never going to have a square root or a cubic root
Actually,
or any
there
kind
is
of root. You
absolutely
don't have
no-
linearity here. So you can work with q squared and you will be fine if you're looking for a model of this. First, this is an axiomatic theory. It's not, there is no model here, but if you're looking for a model, Q squared would be a model.
Okay, because a linear equation, correct.
There are linear
So I don't
equations.
need, I know the need. Okay.
I will then point out that you can see here, this is another set of axioms. This line doesn't show up on the screen. So axiom 8 is actually just the figure. There's no text at all. So this figure actually plays a really interesting mnemonic iconic role in that it's actually replacing all the words. And this is just Vadlin's notes on Moore. There's the intended audience is himself. But it's interesting to see this figure is persisting across these different venues and sometimes even replacing the text. So that sort of episode is maybe more notational, a smaller point, but in fact, it's quite interesting the context in which it emerges. So here again is Moore. And what I want to draw attention to here is not so much the result, but the fact that he then comments, axiom 422, this is one of the parts of his axiom, is a logical consequence of axioms 411, 412, and 421, together with axioms 1 through 3. So and then he actually proves that, he proves that in a footnote. He proves the redundancy of his own axiom, which is really surprising because Moore's whole intention in this paper is to show that there are redundancies in Hilbert. And then he introduces an axiom that he is aware is redundant. And he doesn't then say, so we should eliminate 422. He preserves it for some sort of like symmetry, right? It's aesthetically pleasing, but he knows it's redundant. And so that was quite surprising, which made me then think, well, how important is independence to Moore actually? We tend to associate this paper as Moore creating a more independent set of axioms. He begins this paper by saying there are redundancies in Hilbert, and he proves the result that we discussed earlier, and the paper is known for that. And then even later in life, this is from an obituary of Moore by Bliss and Dixon. They say the papers on postulational foundations were inspired by Hilbert's book on the foundations of geometry of 1899, which attracted the attention of Moore and his students to postulational methods, including earlier work of Pontchampiano as well as that of Hilbert. Moore analyzed skillfully questions which had arisen concerning the independence of Hilbert's axioms. So this work is famous for the contributions to independence, even though Moore is using a set of axioms that aren't independent. And if you sort of revisit Moore with that in mind, you realize that he doesn't actually care very much about independence. He's using it as a motivation, this question of redundancy, but he doesn't give proofs of the independence of his axioms. He relies on Hilbert instead. And he acknowledges this in a footnote. He says, as the independence of the axioms, I'm going to rely on Hilbert, and he sort of discusses that. Each of these proofs involve the exhibition of a particular geometry in which, for example, in the case 9, the relations hold, these certain relations hold while another relation does not hold. This exhibition is in terms of a science supposed to exist without self-contradictions, and the proposition of independence is contingent on the correctness of the supposition. And then you can, when you read his work, you find that he's not actually doing that. He's not exhibiting particular geometry sets. Hilbert does this. And so he's showing certain things are redundant, but then otherwise relying wholly on Hilbert's work. And so this is not a theoretical motivation for Moore in this publication. It's actually quite marginal, despite the fact that this work is associated subsequently with independence, and there are small results about redundancy. Similarly, in the notebooks, this is what I quoted before. Veblen begins, right? So Moore begins by talking about whether the axioms are independent and what is the simplest set of axioms, right? So independence is featured at the beginning of the notebooks, but then if you go through the notebooks, there are no particular geometry showing that a certain set of axioms are independent. There's none of that in the notebooks at all. So independence is acknowledged, it's important, but then it's actually not treated for the rest of the notebook. But Veblen himself became increasingly interested in independence. So sometime between 1901 and 1903, Veblen's interest in independence grows. And so this is Veblen's first publication. It's sort of a literature review on Hilbert's Foundations of Geometry, the work that's been done on it since 1899. And in it, he talks about independence. This is for a broad audience of sort of philosophers of science. So it's not very technical. The sense in which an element is independent of the mental images accompanying it is made clear by the method of proving an axiom to be independent, i.e. not deducible from the others. This is done simply by exhibiting a self-consistent mathematical science in which all the axioms except the one in question are valid propositions, whereas that one is not. For if the indicted axiom were deducible from the others, it would be a true proposition of the new science. So he's defining independence here and talking about how important it is to mathematics. So for a broader audience, he's saying this is an important thing that mathematicians are doing. And then when Veblen first shares his new results, the result of his new research, this is in a meeting of the Chicago section of the American Mathematical Society in April 1903. So about 9 months before his paper is published. And you can see the title actually changes. So his talk in April 1903 is a set of independent axioms of geometry. His published dissertation is a system of axioms for geometry, and the first chapter concerns independence. So this talk given in April is then embedded in his larger project, but clearly independence is very important for him. And we can also see the growing importance of independence if we compare his axiomatic system in the notebooks to what he eventually publishes in 1904. And I talked about this for those of you who were around yesterday. This is what we were looking at, comparing some of these axioms. And so just to briefly go through that, we can think about there being, well, so this is sort of as I was working through comparing this, I identified 4 different statements, which I labeled PQRS. And so the first one, if ABC, then A is distinct from B and B is distinct from C. Q, if A, B, C, then A is distinct from C. R, if A is distinct from B, then there exists a point X such that A be X. And lastly, if A is distinct from B, then there exists a point X such that AX be. So in 1901, his second axiom is both R and S. He folds statements R and S into his second axiom. So these are assumed. And then he proves P and Q with theorems in 1901. And then in 1904, when this is published, he changes this. So he does still keep, so axiom 4, if points A, B, C are in the order A, B, C, then A is distinct from C, so that's Q. But then axiom 5, if A and B are any 2 distinct points, there's this a point C such that A, B, and C are in the order A, B, C. So that is a shift between the two texts. And just to summarize this, so in 1901, we have Q, which is the second statement, is a theorem. In 1904, that becomes an axiom. And then conversely, S is an axiom in 1901, and S becomes a theorem in 1904. So there's a shift. And if you compare these two texts, there are several reasons for this change, but one of them is driven by this desire to have these independence proofs. Because if we prove S as a theorem, that's about existence, and it's going to be more useful for him in showing independence to have fewer assumptions about existence. And he notes this explicitly. It has not been shown as yet that every segment AB contains a point, this is early on, nor that the pair of points AB may not lie on some other line than the line AB. So this is actually before those results. But he's very careful that even though he's talking about a segment AB, he hasn't yet shown by the time of his third theorem that that segment actually has any points on it. That has to be further shown later on. And so you can see this then in this comparison of other theorems. So these are axioms that remain axioms, but the way in which he's stating them changes to put existence in the hypothetical. So in 1901, he just says there exists at least one point X not equal to A or B, such that none of these relations hold. But in 1904, with axiom 7, he's much, much more careful. His axiom just says, if there exist 3 distinct points, so first that hypothetical, then there exist 3 points A, B, C, not in any of the orders. So this addition of the conditional statement is going to enable showing independence of axioms much more easily. And then in theorem 5, he then proves that the line does have a point on it, or does not. And then if you look at his proofs of independence, so just 3 examples. So this is where he's showing the independence of axioms 5, 4, and 1. He does this in reverse order. That's why they're in the reverse order. And you can see that many of these geometries that he's exhibiting, these systems he's exhibiting, consist of very few points. So to show that axiom 5 is independent, he has a system with only 2 points. To show axiom 4 is independent, another system of just 2 points. And then to show his first axiom is independent, he has a system of only 1 point. And then you get many of the other axioms vacuously, because there aren't 3 points, for example. And so this, you can see how the motivation of showing independence is changing the language in which he's using and changing his choice of axioms between these documents over time. The other meta-theoretical concept that emerges between the notebooks and Veblen's publication is categoricity, and this has been acknowledged widely by historians. So Michael Scanlon's 1991 paper on the American postulate theorists says that they developed the notion of categoricity of postulate sets to prove completeness with respect to semantic consequence. And then he says that the notion of categoricity of theories was first formulated by American postulate theorists, was recognized by Tarski, who attributes it to Veblen and Huntington. And then similarly, Aude and Breck look at Veblen among other mathematicians who are some of the earliest contributors to categoricity, along with Dedekind, Peano, Hilbert, Huntington, and Veblen. So it's well acknowledged, it's been established for decades that Veblen was one of the earliest contributors to this concept of categoricity. And as Scanlon notes, this first emerges somewhat informally in this 1903 paper, this more popular discussion, not in the language of categoricity, but actually in the language of a necessary and sufficient set of axioms. So he says, stated in this language, the problem of the foundation of geometry is to find a system of axioms that is necessary and sufficient for geometry. Necessary in that no axiom can be dispensed with, and sufficient for the deduction of the whole system of geometrical knowledge. This idea of sufficiency will then evolve in 1904 to categoricity. So this is his 1904 dissertation. A system of axioms, as we have described, is called categorical, whereas one in which it is possible to add independent axioms and which therefore leaves more than one possibility open is called disjunctive. The categorical property of a system of propositions is referred to by Hilbert in his axiom der Vollständigkeit, which is translated by Townsend into axiom of completeness. And then he also points to Huntington, who has also done work on categoricity, but using different language. Now, intriguingly, the person to whom the term categoricity is due is actually John Dewey, the philosopher. So in a footnote, he says, these terms were suggested by Professor John Dewey, who was at Chicago at this time. And so I think this points to how small Chicago was relatively, that, Veblen's discussing his research with Dewey in the halls. And in fact, if we look at the correspondence, this is also in the Veblen archives, his correspondence with Moore. And so this is just excerpted from a letter from October 28, 1902. So we know Veblen's working on this very project. And he said, Moore writes to Veblen and says, for the Friday Club meeting, please, 1, author our notice is posted. Okay, that's kind of boring. And then 2, urge Messrs. Dewey, Mead, Moore, and others in philosophy to attend and participate in discussion. I expect to be back in time. So you can see that actually the math department is explicitly soliciting the philosophers saying, come to our club. And that's creating this actually really fruitful synergy and developing these meta-theoretic concepts. So it's really nice to see that reflected in the archive and then in Veblen's notes as well, that there's this interdisciplinarity happening. It turns out that categoricity is extremely fruitful for Chicago mathematicians, and you rapidly see a series of articles in which categoricity is foregrounded as an important feature of a set of postulates. So the first example is from Veblen's next publication on analysis situs in 1905, regarding the conditions of definition 4 as a set of postulates for the determination of the notion simple curve. The proposition just proved is in effect that in the presence of axioms, etc., the system of postulates is categorical, and he cites his earlier definition of categorical from 1904. The following year, Bliss, who also had been studying at Chicago, publishes generalization on the notion of angle and says, if it is desired that any two geometries satisfying the initial assumptions shall be essentially the same, the axioms must also form a so-called categorical system, again, citing Veblen's earlier work. 1908, Veblen has a whole chapter dedicated to categorical systems in his text with Veblen with Young on a set of assumptions for projective geometry. And by 1912, Lennis, who had worked with Veblen in various contexts, says, by 1912, it is customary to inquire whether a given set of assumptions is consistent, independent, and categorical. So it's been normalized in this sort of series of 8 years, at least for Chicago mathematicians, right? That they've just seen like this is something that any set of axioms really needs to fulfill. So it's interesting to see that evolution from Veblen coming up with this concept that ends up being quite generative for this local context. And again, Veblen is cited as well as Huntington in this context. So from this last sort of episode and looking at Veblen's notebook, we can see that this axiomatic play in the notebook, this comparison between axiomatic systems, this rearrangement of axioms, is encouraging in a kind of experimentation and an observation of systems. And by observing and comparing systems, this also fosters the growth of these more meta-theoretic perspectives, including independence and categoricity, that we can see becoming more and more important for Veblen between 1901 and 1904. And then, as I mentioned, categoricity in particular proved productive as a research prospect for Chicago mathematicians. There's quite a lot of work in that respect. So I now want to zoom out a bit. I've been focusing on a single text, on a single seminar, and now I want to look actually at just the broader context of Chicago, as well as the postulate theories that were emerging in this context. So this is actually not the only notebook, but it's one of two notebooks that are in Veblen's book. But if you go to the University of Chicago archive, they have more formal notebooks that are taken by a variety of students over decades on a variety of different courses. And we see many of the same features in different disciplinary notebooks. This is a really fancy cover. I don't know who spent a lot of time on this. Not Veblen, although it is worked out by Veblen. Pages 1 through 14 are someone else's handwriting, and then Veblen takes over. But this is certainly not Veblen's handwriting. But if we look at these notebooks comparatively, we can see that there's often a historical narrative that's established in the discipline. This is foregrounding these notebooks. There's also an overwhelming volume of citations to continental European developments, so much so that it's unlikely that all of these texts are actually being engaged with in the classroom. So they're not just playing a role of like, read this, that you'll have like 20 different texts in a single seminar. Unlikely that they're reading the entirety of these texts while taking many other courses. There's also, you can see in many of these notes, progressive efforts towards the best translation from German, Italian, French into English, and then also the best choice of notation. So here you can see Veblen's developing a notation to show line on a line using this vertical line, for example. So there's quite a lot of this throughout the notebooks, this development of new notations. And then another feature that we see across many of the notebooks is that the iterations of several authors on the same mathematics, something that's quite common in the geometry notebook, is resulting in these more meta-theoretic considerations, including things like simplicity. So here, for example, he's comparing a result that's analytical to a result that's geometrical, right? So comparing two of the same thing, but looking at the differences between them. And the use of these notebooks, the presence of these seminars, help shed light on some social features of the Chicago Department of Mathematics. So it was relatively non-hierarchical and collaborative for an academic space in the early 20th century. And especially if you compare it to places like Berkeley, which were much more hierarchical and like what could be quite vicious, in fact. Like students and visitors often commented on being scared of mathematicians in the discussions. So discussions that led to tears. Whereas Chicago seems to be a fairly friendly place, although it was still quite generative, right? So it was less competitive. In the notebooks, you can see interjections between text, professors, and students. So professors criticizing text, students adding to the work of professors, and this interaction between these groups in a way that was quite open. We also see that these seminars were cited, and as well as unpublished graduate student contributions are cited. So Veblen is cited by Moore before Veblen has published anything, which is really, I mean, if you want to be like negative about it, you can be like, oh, he's just trying to boost the reputation of the department. And certainly that did happen. But also he's trying to raise up his student who is still in progress, which is really a remarkable move to say, I'm citing someone who has no record, but I'm showing that they're actually contributing to mathematics before they've published. They also, and Veblen does the same thing with Lennis. He cites his work before Lennis is published. And you can also see this borne out in Veblen's particular career. Among early 20th century mathematicians, Veblen co-authors work at a much higher rate. I know now in mathematics co-authorship is very common, but it was not in the early 20th century. But Veblen co-authors more than he individually authors papers, which is quite unusual. And so the fact that he is coming up in this environment of Chicago is something that he really takes with him throughout his career in working with other mathematicians to develop results. And here is another letter that Moore wrote to Veblen. This is from January 21st, 1903. And I just wanted to highlight here that Moore wants to continue the collaboration that happened, I guess, over a year ago. So he says, let's see. I would be pleased to follow out some plan of direct cooperation in work on the foundations of mathematics. For we both ought, I think, to proceed in this direction, at least for a term of years, and perhaps by joint work we can do considerably better than otherwise. So that's quite nice to find in the archive. But so Moore is really recognizing that the fact they're working together makes their work stronger. And this, I think, is something that Chicago really encouraged as a location. The last thing I just want to say is the fact that this notebook from 1901 is in Veblen's archive shows the importance of this notebook for Veblen, because Veblen died in 1960. And this is one of the earliest documents in his archive. And so he preserved this notebook for 59 years as an important, well, I mean, I said he has 13,000 items. This is one of the 13,000 items that he thought was important. Many of the other items are from the 1930s onward, and they have a much more like administrative tone, right? But this is something that was much more mathematical and personal. And so it just points to the importance of this experience for Veblen throughout his lifetime. So thank you. And now discussion. I thought this was a fun map to end with.
The text discussions, what do you want?
Yeah, I know, amazing.
So I have a comment about this, the fact that it is based on the notion of between, and the definition of the notion or the axioms for intersection is also expressed in terms of the betweenness. It's a true geometry of segments. It's not so much a geometry of lines, right? Of infinite lines. I think you said yesterday that line is definable as a set of points that blah blah blah, right? But line is defined by, it's not a geometry of lines, it's a geometry of segments.
I don't know, because there is if I remember well, that is an action that say for any point A and B, there is a point C that is between A and B,
Yeah.
but there is also a point D that
D.
is between C, that is such that,
Yeah, that is.
such that,
So it is,
C is between,
yeah.
I
It is,
don't remember.
But we still don't have.
There is
line.
one, two,
Two
there is also
of,
something here. So
yeah.
you can prolong it to infinity.
exactly. No, not on infinity. You can.
For any segment, you can construct another one
Exactly.
That's it,
that is longer.
Yeah.
yes.
So there is a potential infinity, not a
Yeah. It's
actual infinity.
like Euclid postulate too.
But the point is, you don't start off with lines as Hilbert does.
Yes.
Correct.
Yeah.
Yeah, he's
Yeah.
following Pierre in this respect. Who he actually visited, and like he has an amazing postcard from Italy where he's like, when the weather's not so good, I go inside and do mathematics.
Questions? Please.
So I was wondering, do we happen to know where Veblen learned projective geometry? Do we have any notebooks from that? Because if you're looking at, I think Moore maybe told something, or Moore was an expert.
Yeah, I think so no notebooks. However, there were courses, and if you look at the courses, there are courses on projective geometry. I haven't checked who was teaching them, but Moore may well have taught them.
Yes, he's the prime suspect.
Yeah,
And I think that's important because if you're looking at, I mean, there's no trace of transformational geometry in here, but still the paradigm is about the central role that the projective geometry plays. And that's exactly inherited from Klein back to 1872, because the target in Moore's work was their projective geometry axioms of projective geometry. This is what he did. And this has to do with the incidence property that you actually have on RP2. And I think that you can find that in Veblen as well. So the question, how was this there should be in curriculum there.
if you're interested in Veblen's reading of Klein, the second part of the notebook, it does concern Klein. I haven't spent as much time with it because it doesn't inform his dissertation, but send me an email, I'd be happy to send it to you.
Absolutely. Here's why I think this is super important, because it's actually the paradigm itself is the paradigm of the Erlangen program hidden in the quest for axioms in geometry, even if apparently we're not doing any sort of transformational geometry, but the very fact that the target is the projective geometry, this is the key element. So it might be hidden somewhere there. That's important.
Yeah. Yes, I mean, I would be delighted to share with you, and then you can tell me what you find, because I haven't given that part of the notebook sufficient time. It's clearly like a later part of the semester, but then they do start looking at Klein's work and also non-Euclidean geometry.
John.
So how did Veblen present his work as something new as an axiomatization? Like was there something thematic about it that he stressed, or is it just very specific details?
So the novel categoricity is actually his main result of what he's showing that's new, is that it's categorical. I don't think he actually says it's the first categorical system, but it's the first one that's being proved as such because it's a new concept. So that's how he's framing his contribution. This is a useful place to talk about it because this is his table of contents on the right. So that's part of it. And then the other, the other feature is that he's showing the independence of all his axioms. I mean, it is a new system. It's not something that people have previously done, but he doesn't point to exactly which parts,
Right, because
which axioms.
there's just a lot of details in the choices.
Yeah, exactly. But yeah, when he's talking about the novelty, it is to show that it's categorical.
But what the categorical, I mean that there is on the model isomorphic.
Yes, he does not talk,
The model,
that concept is, he's not.
what does it
using
mean
isomorphic.
categorically?
Yeah, so the way he's defining it
It's
is,
that the two models are the isomorphic, that what he says here. No? It's part of a proper in more exact language to classes QK of objects satisfy the 12 axioms are capable of one-to-one correspondence, such that if the three element ABC of K are in order ABC, the corresponding element of K are also in order ABC. So this one-to-one is less than isomorphic, because otherwise you should have a second order system, because otherwise you have Lagrange column, so it cannot be categorical. But this seems to me a first order system, not a second order. Why is
He's
it
only ever mentioning finitely many points at a time.
Sorry?
He only is mentioning finitely many points at a time, so I don't
Then?
think. So it's not second order, it might be.
Okay, so
second
how can
order.
it be categorical?
He's quantifying over
No, but then-
finite collections of points, not all
Okay.
points, not all sets of points, but only finite collections of points. So that's second order,
Is it-
it's a weak form of second.
Why? So
He's
if
not-
it's a
He's not
categorical.
quantifying- He's not quantifying over all sets of points. He's only quantifying over all finite sets of points. And that's a weaker system.
No,
It means-
that's not it.
It means that any two finite models are isomorphic, is what you mean?
Yeah, because he only mentions finitely many points at a time.
It's a very weak form of categoricity.
I think so. Because he doesn't have a model other than that. So
Well,
let's
otherwise,
go back. So
There's a comment by Victor. He's calling on Zoom.
Yes.
Yeah,
Can you speak up?
yeah,
Victor, can you-
I can speak. I hope I'm heard. I don't know.
No,
Yes, wait a second, it's a little bit, the volume is a little bit low, let me try. Can you speak?
Yeah,
Yes, thank you, now we can hear you.
okay, so there are a few things I wanted to say. First of all, the stuff with the transversal. Those are essentially two axioms. I don't know where the four are coming for, but anyway, these two, the difference with the Pasch axiom is that they're valid regardless of dimension. Pasch said, well, if a line enters a triangle, it has to exit it. Well, that already in itself contains an upper dimensionality axiom. These two versions that were presented do not contain that. And they go back to Peano. In 1889, their axiom 13 and 14 in Principi di Geometria. So Veblen, the important part of this is not the categoricity, because this stuff, as pointed out here, in 1904, there was complete confusion about an axiom system and what do you want to do with it, because there was no concept of first order logic. So in Hilbert, you have also this heavily higher order axioms, and Veblen has the same thing with the categoricity. But if you ignore that, which comes towards the end of the paper, it is full second order logic because he needs continuity to get this thing going.
Mm-hmm.
But if you ignore that, which is, as I said, after 1930, is no longer in any serious axiomatization. All serious axiomatizations after that are first order. So the categoricity thing is no longer of any interest. Or to put it with Jose Ferreiros, I mean, if you want to axiomatize something, then there is no other way than first order logic to do it. Anything else is basically, you better describe the models. What's the point of axiomatizing? So what the importance of this paper is, say for later on, not for what he thought was important, is that he proves all these, the 4-point thing that was pointed out. And then he shows that one of the two forms of the Pasch axiom, which, as I said, go back to Peano, today they are called the inner form of the Pasch axiom and the outer form of the Pasch axiom. He proved that the inner form follows from the threefold application of the outer form. He also claims mistakenly, without any proof, because, well, there couldn't be any proof because it's a mistake, that you can deduce outer Pasch from inner Pasch. Well, that's false. You can't actually. So, but he showed that threefold outer Pasch gets you inner Pasch, and that's the first time that this was done, because as I said, in Peano, both were needed. So whereas after Veblen, you know that you don't need inner pash. It's enough to have outer pash. So that's what a look at this thing from later on. I mean, in its time, obviously he thought that this categoricity business is of any significance. But if you look for later on, this is what stuck. And that's all I wanted to say.
Thank you. I took some notes. That's really useful. Yes, I was relying on Veblen's own words of what he thought was important.
It was a
One
little
isn't
bit
always right.
difficult for me to understand. So what is the point about categoricity?
My point was that categoricity comes from Hilbert, who wanted to give this axiom system for one model.
Yes, but in Hilbert, the system is categorical because there is the last axiom that says that the model is the maximal one. So in some sense, the fact that the system is categorical is an axiom. The axiom of continuity is the axiom saying the system is categorical. Okay, that is very easy to have a theory that is categorical if you have an axiom that says that the theory is categorical.
Yes, but I mean, you don't, even if you have continuity, it's going to be second order. And for philosophical
Yes, but if you eliminate the last axiom from Hilbert, the axiom of optimality of the model, the system is not categorical.
That is exactly what I was saying.
R2 as model of also Q, what extension of Q that you want. So in Hilbert is highly not categorical without the last axiom that Hilbert explicitly say is not fundamental. We can add here for elegance, but we could eliminate. And if we eliminate the last axiom, the system of Hilbert is not categorical.
Yes, and what I was saying is that the later development of the foundations of geometry, once it was established what first order logic is, so sometimes in the 1920s with the work of Scoulem and so on, the whole thing about categoricity became obsolete because it's not interesting in axiomatizing categorically things, because if you do so, you may as well introduce them the way they're introduced in classes. This is the set, these are the elements, and that's it. You don't need to go through the axiomatization, because what's the difference? If you assume set theory as your foundation, then you gave up the interesting part of the project. But as I said, at the time, in 1901 and 12 and so on, this stuff wasn't clear at all. So they thought that this is something really interesting.
And that's I understand. What I do not understand very well, but possibly not because you do not explain well, because the sound for and not English is not clear. It's not completely clear. So there are some words that I simply do not understand the English. So what I do not understand is in which sense the system of Veblen is categoric.
In the sense that it has a single model.
Yeah, this is what it says there. It says there.
That all models are
Essentially one class.
Sorry, essentially?
I can read.
Line number 4 or 5.
It is part of our purpose, however, to show that there is essentially only one class of which the 12 axioms are valid in more exact language, and into classes K and K prime of objects that satisfy the 12 axioms are capable of a one-to-one correspondence such that if any 3 elements ABC of K are in order ABC.
So why is it
correspond
not
elements-
contradicted by Lovenheim's column? Because it's the model finite?
No, but because he assumes the axiom of
The
the completeness axiom.
Where is the completion axiom?
In the second paragraph towards the end.
The axiom 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12. 12.
axiom 12, this is a okay. So there is a but where is it? Yeah, it's not here. Where it is?
No, the axioms are not here in this page.
Okay. So we have an axiom of completeness. Okay. That's I did not understand. Okay. Then it's easy. Okay. So in some sense, it's categorical because the axiom says that it's categorical.
Yeah.
So what is the interest of?
And
And that's Victor's point.
Okay. Now I understand your point, Victor. Oh, thank you.
Would you help if we come up with an example of something that is not categorical as a system?
For me?
No, in general.
Oh,
Oh, that's easy.
Is the Hilbert neutral?
Well,
Hilbert neutral.
Just eliminate the parallel function.
That's it.
Yeah,
That's all.
if you have, as by Löwenheim-Skulem, if you have a first order axiom system and it has any infinite model, it will have infinite models in all cardinalities. So you're very far removed from,
Yes, exactly.
yeah.
Yes. Okay, now I understand your point. Okay, sorry. Other questions? Go.
What does he mean by method? What does Veblen means by, and here's what I'm thinking. If you're thinking historically, the very definition of metric was actually elaborated about the same time, beginning of the
Frechet or something?
Frechet, you're right. It's Frechet, I think, what was that, 1903,
Yeah,
1904?
very close.
So what is the meaning of metric geometry? Because today we understand, I mean, it's a space endowed with a metric and we have the axioms and so on. But there, the very idea of it is going like projective and metric geometry. If you look at the summary, the last part of his paper, that's
okay.
there's another interesting thing that could be placed into context and investigated. Because again, it's that decade when everything was defined and the concepts were taking shape.
Yeah. Are you seeing metric on this page? Are you referring to?
No,
a different-
no,
Okay.
If you
the
go to
table
the
of
summary,
Okay.
part 3, the title is
thank you.
projective and geometry,
Yes.
and you wonder like, what in the world is he understanding?
Yes, and
Well,
I
This,
sorry, yes, go ahead.
this part is again leading to a lot of confusion, and this was the same with Huntington, because these people thought that you could do everything with just order, because you would get congruence, like the metric, for free. Well, why would you get it for free? Well, because your axiom system is categorical, and then you can find a projective metric inside projective geometry the way Klein or Cayley did it. So, but does it say anything? No, because order is not, congruence is not definable in terms of order in a first order manner. So that part is the least interesting today. The interesting part is the first chapter, actually.
Okay, thank you for that.
Okay. Other remark, objection, criticism, protestations? No? Victor, other remarks?
No, none.
Okay. So, Victor, there is something that is not good in all that you cannot come to drink a beer with us. Now we go for a beer, but do you want to take a plane and you come?
No, I'm not drinking beer anyway.
Okay. So next year you come, Victor, okay?
Hey.
Okay, good. You are already invited, and then we will find a date. Okay, so thank you for all of you. Thank you, Gemma.
Yeah.
And